Hello everyone, welcome into another lesson. So today we're going to talk about some theorems involving parallel lines. And up first, we have a theorem here that states if two lines are parallel, then all points on one line are equidistant from the other line. So here we have lines L and M. They are both parallel to each other. And then we have points A and B on line L, points C and D on line M. What that theorem is saying is that from A to C and B to D, those distances would be equal. So AC would be congruent to BD. That's what this theorem is really saying. And the true distance from a point to a line is the perpendicular segment from one line to the other. That would make the segment from the point to the line perpendicular. So that's the true distance from a point to a line. So again, if two lines are parallel, such as L and M, then all points on one line are equidistant from the other line. So points A and B would be equidistant to points C and D. So AC would be equal to BD. In fact, we're about to prove that real quick. This will be the only proof in today's lesson. That's all we're going to do with this theorem, because I have three more theorems that we won't do proofs for. But I think this is a good one to prove. So we are given that L is parallel to M. We are given that. A and B are any points on L. That's something we were given. Then we're given two more things. We're given that AC is perpendicular to line M. We're also given that BD is perpendicular to line M. So what are we going to prove? Well, we're about to prove that AC is congruent to BD. So we're going to prove that AC is congruent to BD. So this will kind of be incorporating everything we've learned so far into this proof. So let's go ahead and set up our columns here. So we have our statements and our reasons. All right, so I think in this case, we're going to list all the given information in statement 1, that L is parallel to M. A and B are any points on L AC is perpendicular to point M, to line M, and then BD is also perpendicular to line M. So of course the reason for statement 1 is that was given information. So that's been given to us. So what do we do with this given information? Well, we can also say that for step 2, C and D are on M. That was also given to us in the diagram. So for step 2, that's given. Now, where do we go from here? So we've established that A and B are on L, and then C and D are on M. Okay. Where do we go from here? Well, by extension, if L is parallel to M, that would have to mean that line segment AB is parallel to line segment CD. But what would be the reasoning? Because if AB is on line L, and then A and B are on line L, C and D are on M, while L's parallel to M, that would have to mean that line segment AB is parallel to CD. We can also say that was given. That was actually kind of given to us because based on the diagram we figure out the points, each of the points on the line. If the whole line's parallel to the other line, that means the points on one line are parallel to the points on the other. So let's actually go ahead here. We'll set up congruency markers for that. Not congruency, parallel markers. So now we can say that AB is parallel to CD. What would be next? Well, I think the next thing we can soundly say is that AC would be parallel to BD. That would be step 4. So AC would be parallel to BD. Well, how are they parallel? It all goes back to that theorem that says two lines perpendicular to the same line are parallel to each other. So here we see that AC is perpendicular to line M. Well, BD is also perpendicular to line M. That means they have to be parallel to each other, right? Two lines perpendicular to a third line are parallel. That would be the reasoning for step 4. Two lines perpendicular to a third line are parallel. So now we can actually place parallel markers on AC and BD. So what do we have here now? This is going to be interesting. We have that both pairs of opposite sides, AB and CD, are parallel, as well as AC is parallel to BD. By definition, that would have to mean that ABDC is a parallelogram. ABDC is actually now a parallelogram. That's simply based on the definition of parallelogram, because you have both pairs of opposite sides parallel. So the definition of parallelogram would prove that ABDC is actually a parallelogram. Which means now, if we can prove this quadrilateral is a parallelogram, we can go ahead and prove that AC is congruent to BD. How so? AC is congruent to BD by the theorem that opposite sides of a parallelogram are congruent. So let's go through this proof real quick. We were given our diagram here. We were given that line L is parallel to line M. We were given that A and B are points on line L. We were also given that segment AC is perpendicular to line M, and that segment BD is also perpendicular to line M. That was our given information. And then we can use the diagram for statement 2 that C and D are on M. That was also given to us by the diagram. So we were able to deduce for step 3 that AB is parallel to CD, because points A and B are on line L, and then points C and D are on line M. So therefore, both points on one line are parallel to the points on the other, so AB is parallel to CD by given information. Now, from there, we were actually able to determine that AC is parallel to BD by the fact that two lines perpendicular to a third line are parallel to each other. So AC was perpendicular to M. BD is also perpendicular to M. That means AC would have to be parallel to BD. Next, we were able to prove then that ABDC is a parallelogram by the definition of a parallelogram, because you have both pairs of opposite sides of the quadrilateral are congruent. And then last but not least, we could prove AC is congruent to BD because opposite sides of a parallelogram are congruent. So that's the proof of the theorem that we just got that stated if two lines are parallel, then all points on one line are parallel to the other line. So that's all we're going to do with that theorem today, and you can keep that in your toolbox and you can use that for other proofs in the future. So that might help you in the future. Now, let's see here. Let's do another theorem. Here's the next theorem. If three parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. And I'm going to illustrate that real quick, then we're going to do some exercises with this theorem. So if three parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. So let's draw some parallel lines here. Draw three parallel lines, okay? Let's see. This would be point A, this would be point B, this would be point C, this would be X, Y, and Z, where the transversals come together. So what this theorem here is really stating is that if you have A and B and C congruent, right? They cut off congruent segments on one transversal. That means XY and YZ will also be congruent to each other. That's what that means. So that's all that means. And now we're going to put this theorem into practice with some exercises here. So let's go ahead and do just that. Okay. This time we have four parallel lines, which this theorem works for three or more parallel lines. You can totally have four. There's no rule against that. Here's point A, here's point B, here's point C, here's point D. This one goes straight up. Here's point E, here's point F, G, and H. We are given that each of these lines is parallel to each other. All right. Now, what we're about to have to do, they're going to give us here for this problem, if AB equals 5, then AD equals, okay. So for this particular exercise, they give us that AB is equal to 5. So let's put 5 next to that here, right? Well, we know then that these are all congruent segments on each transversal, right? If AB equals 5, well, that means BC would have to equal 5 also if they have congruent segments, which would mean that CD would also equal 5, would it not? Okay. Well, to solve for AD, we need to use the segment addition postulate. We know then that AB plus BC plus CD therefore would equal AD, right? Well, AB is 5. This translates into basically 5 plus 5 plus 5 would equal AD, therefore giving us an answer that AD would equal 15. So the length of segment AD would end up being 15. Because on each of these transversals, there are congruent segments on each. So we just use the segment addition postulate of AB plus BC plus CD to equal AD. So it turned into 5 plus 5 plus 5 equals AD. So AD would equal 15. All right. Going to keep the same diagram, but it's going to change up a little bit. Let's see what they give us here next. Let's see. If, let's see, AC, the whole AC is 12 this time. So if AC equals 12, then CD equals what? So we have that the whole segment AC equals 12, then CD equals what? Well, isn't it true that AB plus BC equals AC, right? Well, at that case, then AB plus BC equals 12. Well, we know these are congruent segments. So that means we can say AB is congruent to BC. So really, we can substitute AB in for BC. So you just end up getting 2AB equals 12, which would then just give you that AB equals 6. So AB itself would equal 6, which means since AB and BC are congruent, BC would also be 6. And then if these are all congruent segments on this transversal AD, that means CD would have to equal 6. So Therefore, that leaves us to conclude that CD would also equal 6. So the answer you would get for CD is the fact that it equals 6. And I got even more. Wait, why am I erasing point A? That don't make any sense. Wrong color, dang it. There we go. That's more like it. Alright, so what's next? If AB equals 5x, and BC equals 2x plus 12, then x equals what? What does x equal then? Well, something to know here. Again, each of these transversals are cut into congruent segments, right? These parallel lines cut congruent segments on each transversal. So AB, that's 5x. BC is 2x plus 12. Okay, so we know that congruent segments means that they're equal to each other. So in other words, AB would equal BC, which would have to mean then that 5x equals 2x plus 12, which would simply mean that 3x equals 12, which would then give you that x equals 4. So the answer to this particular one is that x would equal 4. And if you plug the x value in for each of these equations, you would get a length of 20 and a length of 20. So that actually totally checks out. All right, what we got here now? If AC equals 22 minus x, and BD equals 3x minus 22, then x equals, okay, so what are we going to do here to solve this, right? We have that AC equals 22 minus x and BD equals 3x minus 22. Then what is x? Well, here's something to consider. So what do we know then? That AC would simply equal AB plus BC, right? So AC equals AB plus BC. And in fact, if we have congruent segments on every transversal, that means AB is congruent to BC, which is actually also congruent to CD. So all three of these segments are congruent to each other. So now we can also say that BD is equal to BC plus CD, right? Well, if all three of these segments are congruent to each other, what does that mean? That means for CD, we could substitute AB in here if we want to, right? Because it's congruent. So we can actually say then that BD is also equal to BC plus AB. Well, it would be true then that AB plus BC is equal to BC plus AB, right? Which then proves what? We can substitute each of these for AC equals BD. So now we've proven that AC equals BD. So at this point, we can take that 22 minus x, set that equal to 3x minus 22, which would end up giving you 4x equals 44, which would then give you that x equals 11. So how did I do that again? Well, for starters, on each transversal, the three segments are congruent. AB is congruent to BC, which is congruent to CD. So what I did is I used the segment addition postulate for AC, which would be the sum of AB plus BC. I also used it for BD, which would be the sum of BC plus CD. And then I used the fact that AB is congruent to CD to replace the CD with AB in the BD equation. So BD equals BC plus AB, meaning that AB plus BC equals BC plus AB, which then I could just substitute AC equal to BD. So then I was able to prove that these two were congruent, which means I just simply set their values equal to each other. I come up with the fact that x equals 11. All right, what do we got next? Two more. If AB equals 15, BC equals 2x minus y, CD equals x plus y, then x equals what, y equals what. So this time we have to solve for both x and y. Again, we know that each segment of this transversal, these four parallel lines, cut three congruent segments on each of these transversals. So let's go with what we know. AB is 15, BC is 2x minus y, and then CD is x plus y. Well, if all these segments are congruent to each other, we're going to get a nice system of equations. So all you got to do is take BC, set it equal to AB, so that would give you 2x minus y would equal 15, right? That would also give you x plus y equals 15. So we've just created a system of equations here. And I think with this system, it's pretty obvious. We just want to go ahead straight away and add the second equation to the first, because that's going to cancel out the y's. You would just end up getting 3x equals 30, which would have to give you that x equals 10. So now all we have to do is put that value of x into one of these equations and solve for y. So we'll put in 10 plus y for the x plus y equals 15, which simply means that y equals 5. That's really all that means. So you would end up getting then that x equals 10, y equals 5. And if you stick in each value into these equations, it checks out. You would get 15 for BC and 15 for CD. I got one more with this theorem. And then I got two more theorems that we're going to kind of combine into the same exercises because they go hand in hand. Let me erase this here. All right, what's next? If AB equals 12, BC equals what? 2x plus 3y BD equals 8x, then x equals what? Y equals what? Very interesting equation. So if these are all congruent segments, right, on this transversal, so that means AB, again, is congruent to BC, which also means that BC and AB are both congruent to CD. So let's establish that real quick. Well, AB is 12, BC is 2x plus 3y, so I think it's safe to say we can establish our first equation in this system as being 2x plus 3y equals 12, right? We can definitely establish that as one equation in the system we're about to have to solve. But what do we do with the information that BD equals 8x? Well, if BC is congruent to CD, right? That means that at this point, BD is double CD, right? So if BD is 8x, that would have to mean CD is half of that, which would give you 4x. If the whole BD is 8x, while CD is half of BD, that would have to give you 4x, wouldn't it? We can also use that 4x equals 12. Well, this turned out not to be such a big system after all, right? We just solve for x. You would end up getting x equals 3. So what about y? Plug that into the first equation. So 2 times 3 plus 3y equals 12. So that gives you 3y plus 6 equals 12, which then gives you that 3y equals 6, which would have to mean that y equals 2. So what you should get is that x equals 3 and then y equals 2. Let's test it out here. You'd have 12 here for CD if you put in the x there. So yes, that would match AB. What about BC? So 2 times 3 is what? 6. And then 3 times 2 is 6. So yes, BC would also be 12. So the fact that x equals 3 and y equals 2 would actually check out. So sometimes they try to trick you by giving you a double segment, so be mindful of that. Alright, I have a couple more theorems here. I'm going to write them both next to each other, and then we're going to put them into practice with the next few exercises. Alright, so let's do the first theorem. A line that contains the midpoint of one side of a triangle and is parallel to another side also contains the midpoint of the third side. I'll talk about both the theorems I'm writing here in a minute because I'm going to draw a diagram afterwards. Alright, the next theorem, the segment that joins the midpoint of two sides of a triangle, and this is a two-parter for this one. For step one, part one of that is parallel to the third side. Step two is half as long as the third side. Okay, so let me draw my diagram here. Let me put up some congruency markers here for this. Alright, so first theorem. This triangle will be used for both theorems. A line that contains the midpoint of one side of a triangle and is parallel to another side also contains the midpoint of the third side. So here you have triangle ACD. You have triangle ACD, right? Well, for sure, here, line BE, line segment BE contains the midpoint of AC. B is the midpoint of AC, so AB and BC are congruent. It's also parallel to the base of the triangle CD, so it's parallel to the other side, means it contains the midpoint of side AD. So that means AE would be congruent to DE. That's all that theorem states. The next theorem using this triangle also is the segment that joins the midpoint of two sides of a triangle for part 1 is parallel to the third side. So segment BE joins the midpoints of AC and AD, right? That means that BE would then be parallel to CD. Part 2 of this is that this segment BE would be half as long as the third side. So in other words, BE would be equal to 1/2 of CD. That's what that means. And BE is half as long as CD. So we're going to put these into practice with some exercises also. All right, what's next? What do we got for the exercises? We have a couple exercises with this here. We'll have about 6 exercises. So let me draw a couple triangles. This is a funky looking one. Alright, really funky. I'm even going to shade the regions. So let's see. This is point X. Here's A, B, C, D, E, F, and Y. Let me shade in these respective triangles here. They ain't going to be perfect, but I'm going to color these two triangles stacked on top of each other, right? Let's make them a nice Christmas color. Probably because it's my favorite season. Okay, so these two triangles should now become easier to see. Alright, so what we're going to do is put these theorems into practice that we have just discussed. This is going to be more finding values. So, in this case, if CD equals 24, then AB would equal what? EF also. We also need to figure out EF. Alright, so we're given then that each of these here, AB, the line AB contains the midpoints of XC and XD, and then the line EF contains the midpoints of YC and YD. That'll be true for the next 4 exercises that we do, okay? We're given that CD equals 24. Well, first, let's start with AB. What would AB equal? Well, the line that contains the midpoint of two sides of a triangle, we know, is part 1 parallel to the third side. Part 2, it's half as long as the third side. So what this really means is that AB is equal to half of CD, right? Which would mean then it's equal to half of 24. Well, we know half of 24 is 12. So AB would have to equal 12 by the theorems that we just learned. Now, we've dealt with triangle XCD. What about triangle YCD? Well, notice they both share the same base with CD. They both share the same base, don't they? They intersect there. That also means that EF, since it connects the midpoints of YD and YC, it's parallel to CD and it's half as long as CD. So EF is also equal to 1/2 of CD, which therefore means it's equal to half of 24, which then means what? That EF would have to equal 12. So the answer is then that EF and AB, both of them equal 12. So that wasn't so bad. Move on to the next exercise. What's the next one? Good one. If AB equals K, CD equals what? And we also got to find EF. I almost cut it short. So we're given that AB has a length of K. Well, what does CD equal? It would be, we also got to figure out EF. Well, again, AB contains the midpoints of XC and XD, right? That means that AB is equal to half of CD. So, in other words, AB equals half of CD. This time, AB has the value, so that means half of CD equals K. Which, if we want to solve for CD, we just multiply both sides by 2. You would get that CD equals 2K. So now we've been given the value that CD equals 2K. So all that's left to do now is solve for EF. It's the same scenario with triangle YCD. EF contains the midpoints of YD and YC, so therefore EF is half as long as CD. So EF equals half of CD, which then means it's equal to half of 2K, which also means that EF equals K. So we get that CD would equal 2K and that EF equals K. And by now you should be noticing a pattern that both AB and EF would be equal to each other. And that's actually going to continue to be the case for the next two exercises. So we'll go ahead and get into those real quick. That fact's going to come in handy then. We can establish, based on the past two exercises, with inductive reasoning that actually holds, this time it actually holds that AB is equal to EF, right? I'm going to write that fact up here since we've now established that. Alright, so what's the next one? If AB equals 5x minus 8, and EF equals 3x, then x equals what? Well, let's start with the fact that we can establish that, first off, line CD is the base for both of these triangles, right? And that since both AB and EF are both equal to half of CD, then that means AB has to equal EF, right? Well, this fact is about to really come in handy with this one. If we have that AB equals 5x minus 8 and EF equals 3x, since they're equal, all we need to do is set them equal to each other. So AB equals EF, which then means that 5x minus 8 would equal 3x. Which would then just give you that 2x equals 8, which means that x equals 4. And if you put these values in, you would end up getting, what would you get here? You would end up getting 12 for each of them, so that would check out. And I got one more of this type, and then I got 2 more exercises after that. What's the next one? So, if CD equals 8x and AB equals 3x plus 2, then x equals what? Okay? I can actually take this one down now. Because what? Okay. So we're given here that CD equals 8x, right? AB equals 3x plus 2. Well, once again, AB contains the midpoints of XC and XD, which means that it's equal to half the length of CD. So AB equals half the length of CD, which AB is what? 3x plus 2 equals half of what? CD was 8x. So we get now that 3x plus 2 equals half of 8x, which would have to give us that 3x plus 2 equals 4x, which could only mean then that x equals 2. So by that, we get x equals 2. Alright, I have just 2 more exercises. This triangle's done. Let me draw 2 more triangles here. Well, I'm going to draw 1 triangle to start with. Okay, so in this exercise, we're going to find the values of x and y, okay? Well, the segment here in the middle of the triangle joins the midpoints of both sides. So let's start with what we know about, let's start with solving for x. If this middle segment in the triangle joins the midpoints of both sides of the left side and the right side of the triangle together, that means it's equal to half the third side, half the base. So to solve for x, we're going to take the fact that 3x plus 5 would equal half of that 12x minus 8. It'd be equal to half of that, which then means that 3x plus 5, when we do the distributive property, is equal to 6x minus 4, which would simplify into 3x equals 9, which then means that x equals 3. So to solve for x, I use the fact that this, you know what, it would probably help if I drew congruency markers, wouldn't it? It joins the midpoints of both sides together, which means then that this 3x plus 5 segment is equal to half of the base, which then we do the algebra means x equals 3. Now, the y is actually going to be simpler because on the right side here, both segments are congruent, right? You have two congruent segments, so all you're going to do to solve for y is take 4y plus 2, set it equal to 7 times the quantity of y minus 1. Which then when we do the distributive property, 4y plus 2 would equal 7y minus 7. Which would turn into 3y equals 9, which means that y is also 3. So, using what we've learned so far in some algebra, x equals 3 and y equals 3. And I got just one more exercise and we're done for today. All right, what's the last one look like? For good measure, let's establish here that this middle segment joins the midpoints of both of these sides, right? Okay, so this side is 5x minus 3y. This side here is 7. This side here is 3x minus 2y. This side here is 8. Alright, so we're going to have some fun here for a second. It doesn't really matter which order we start in, to be honest with you, because we're going to get a system of equations. Let's start with the 7 and 5x minus 3y. We have established that the segment that has a length of 7 joins the midpoints of both of these sides, right? Okay. What that means is that the 7 would be equal to half of the 5x minus 3y, right? That's not so pretty to deal with when you have a fraction, is it? Wouldn't it be easier if we just multiplied both sides by 2? Sure it would. If we did that, you would just simply get the fact that 5x minus 3y equals 14. So since this side is half of this, you can argue that this side is twice that by what we just did. That makes sense, right? So we have 5x minus 3y equal to 14. Now here, the 7 segment joins this side at the midpoint, so that means 3x minus 2y would have to equal 8. So 3x minus 2y equals 8, does it not? Well, this is going to be another fun system of equations because we have nothing we can readily cancel out, not without doing some multiplication. I'm going to suggest we go for the y variables to cancel out because we'll probably end up working with some smaller numbers if we do that. So you're going to want to multiply the first equation by 2 to get a 6y. So multiply your first equation by 2. Then multiply your second equation by 3 to get a 6y, so you can hopefully start canceling them out. If we do that, 2 times 5x, you get 10x minus 6y equals 28. And then you get 9x minus 6y equals 24. Alright, so here both equations have a negative 6y, do they not? That means if we subtract the second equation from the first, we're going to be good to go. We'll end up canceling out the y term. So let's go ahead and do the subtraction. 10x minus 9x is just x. Negative 6y minus negative 6y goes to 0. That's going to equal 28 minus 24, which is 4. So right away we get that x is 4. Now to solve this system of equations, all we have to do is put in the x value for one of these equations. I'm going to do it with the 3x minus 2y equals 8. So 3 times x is 4 minus 2y equals 8, which would give me 12 minus 2y equals 8, which would then mean that negative 2y equals negative 4, which then means that y equals 2. So in the end here, by using the theorems that we've learned and doing the system of equations, you get that x is 4 and y is 2. So that's all I have for this lesson about the theorems involving parallel lines. The next lesson, we're going to get back more into parallelograms. We're going to talk about 3 other types of special parallelograms. So I hope everyone has a good day. Take care.